On October 4th, 2021, Facebook vanished from the internet for 6 hours. Not because of a hack, not because of a hardware failure, because of a routing protocol you've probably never thought about, the Border Gateway Protocol, BGP. At 15:39 UTC, BGP withdrawal messages started leaving Facebook's backbone. Within minutes, every router on the planet had been told the same thing. The IP prefixes that hosted Facebook's DNS were unreachable, so the addresses for Facebook.com simply stopped resolving. 3 billion users, WhatsApp, Instagram, Messenger, all of it gone at the same moment because of a few protocol messages. In the next 10 minutes, we're going to understand exactly what BGP is doing every time you load a website, why it works, why it's so fragile, and how a few lines of routing config managed to make Facebook disappear. Here's the secret nobody tells you in networking class. The internet is not one network. It's a federation. Roughly 100,000 independent networks, each called an autonomous system, or AS for short. Your ISP is an AS. Google is an AS. Cloudflare is an AS. Each one has its own ASN, its own routers, its own internal policies. Inside an AS, the operator picks whatever interior routing protocol they like. OSPF, ISIS, eIGRP, static routes, their network, their rules. But the moment a packet has to leave one AS and enter another, those interior protocols stop. They don't speak each other's language. They don't trust each other. So we need a different kind of protocol, one that runs between ASes, one that's the common language of every network operator on Earth. That protocol is BGP. So how does BGP actually work? At the wire level, it's surprisingly simple. 2 routers in 2 different ASes set up a TCP connection on port 179. That session stays open. As long as the link is healthy, BGP keeps the conversation going. Once peered, they exchange update messages. Each update says 3 things. Here is an IP prefix I can reach. Here is the chain of ASes the route has passed through, called the AS path. And here is the next hop address you should send the packets to. The receiving router takes that information and stores it in its routing information base, the RIB. Now it has a route. If a better one shows up later, the router replaces it. That's the whole protocol. Persistent TCP sessions, updates and withdrawals, routers gossiping reachability with their neighbors, one prefix at a time. Here's where BGP differs from almost every other routing protocol you've seen. BGP is what we call a path vector protocol. The route announcement doesn't carry a metric. It doesn't carry a hop count. It carries the entire chain of ASes the announcement has traveled through. When AS-D originates a prefix, the AS path is just the list with one entry. D when AS-C learns the route from D, C prepends itself, and the path becomes C. D when B learns it from C, the path becomes B, C, D. Each AS adds itself before passing it on. This gives you loop prevention almost for free. If any router ever sees its own ASN already in the AS path of an incoming announcement, it drops the route on the spot. There's no count to infinity. There's no timer waiting for the loop to die. Just look at the path. If you're already in it, ignore it. In the real world, a BGP router usually learns about the same destination from several neighbors. Multiple paths to the same prefix. So how does it pick one? BGP runs a deterministic best path algorithm, and the very first rule isn't shortest path, it's highest local pref. Local pref is a number the operator sets. It's their way of saying, I prefer this neighbor over that one, regardless of how the route looks. Highest local pref wins, period. If local pref ties, then BGP looks at the AS path length. Shortest path wins, 3 ASes beats 4 ASes. Still tied, it checks MED, the multi-exit discriminator. Then external paths beat internal ones. Then lowest IGP cost to the next hop. Then router ID tiebreaker. 5 rules, sometimes more. The point, BGP doesn't pick the shortest route. It picks the best route by policy. And policy almost always wins over distance. So if it's not distance, what actually drives the policy? The answer is money. Inside an ISP, every BGP neighbor falls into one of three categories: customer, peer, or transit. Your customers pay you. Every byte you carry for them earns revenue. Your peers exchange traffic with you for free. That's called settlement-free peering. And your transit providers are the bigger ISPs above you. You pay them. So the routing policy almost writes itself. Set the highest local pref on customer routes. Forwarding their traffic makes you money. Set medium local pref on peer routes. They cost nothing, so use them when you can. And use transit routes only when nothing else works, because every byte you send through transit costs you. The traffic flow of the entire internet is shaped, in large part, by who is billing whom. BGP is the protocol that lets the contracts become routing decisions. There's a problem at the heart of BGP. It trusts what its neighbors tell it. When an AS announces an IP prefix, every other router on Earth, by default, takes its word for it. There's no built-in cryptographic proof. There's no central authority saying, yes, this AS is allowed to originate this prefix. It's just trust between operators. In April 2018, an attacker exploited that. An AS in Ohio briefly announced IP prefixes belonging to Amazon's Route 53 DNS service. Routers around the world believed it. For about 2 hours, traffic that was supposed to reach Amazon got rerouted through the attacker's network. Some of that traffic was DNS lookups for MyEtherWallet.com. The attackers responded with a phishing page. Users entered their wallet seed phrases. The attackers walked away with about $150,000 in Ethereum, all from a few BGP update messages accepted on faith. The fix for that trust problem is called RPKI, Resource Public Key Infrastructure. The idea is straightforward. The legitimate owner of an IP prefix publishes a signed certificate called a Root Origin Authorization, or ROA. The ROA says this prefix may be originated by these specific AS numbers, and only those. Routers fetch these certificates from a validator and keep them in a local cache. When a BGP update arrives, the router compares the origin as in the update against the signed ROA for that prefix. If they match, the root is valid. If they don't, the root is invalid and gets dropped. It's not a complete defense. RPKI only validates the origin, not the entire path, but it shuts down the most common kind of hijack. As of 2024, most major networks enforce ROV, root origin validation, on routes from their peers. Hijacks still happen, they're just much harder. Now we can finally read the Facebook postmortem. At 15:39 UTC, Facebook engineers pushed a routine config change to the backbone routers. A bug in the audit step incorrectly judged the entire backbone as unhealthy. The routers responded the way BGP says they should respond when their links go down. They withdrew their routes, including the routes to Facebook's own authoritative DNS servers. Other ASs around the internet honored the withdrawals. They correctly removed Facebook's prefixes from their tables. From the outside, Facebook had simply stopped existing. But here's the worst part. Facebook's internal tools, chat, the on-call paging system, even the badge readers on the data center doors depended on Facebook DNS to resolve internal host names. The engineers who needed to revert the change couldn't log in to fix it. Someone had to physically drive to a data center, and once there, get past locked doors that no longer recognized their badges. 6 hours later, the route was back. So that's BGP. Routers in different networks set up TCP sessions on port 179. They exchange update messages. Each route carries the full chain of ASs it has traveled through. They pick paths by policy more than by distance. And the whole system runs on trust between operators, with RPKI slowly hardening the edges. BGP is old. The current version, BGP4, is mostly defined by RFC 40-271 from 2006. The global routing table now carries close to 1 million IP4 prefixes, every cloud region, every CDN edge, every multi-homed business. They all run BGP. It's fragile. It can take down a service the size of Facebook with a single config push. And yet, it's been holding the internet together for over 30 years. the protocol you'd never heard of, quietly running underneath everything you do online. Thanks for watching.